Okay, good morning. This is Professor David J. De Los Reyes. It's August 24, 2023. The time is 2:45 a.m. Okay, my long video format discussion for this morning will be alternating current circuit, and this is a continuation, lesson number 29. And lesson number 29 is example of Nodal's theorem using three voltage sources of MF. The last time around, I give you example problem on how to compute for the load current if we are given two voltage sources. For tonight, it's much worse. It's three voltage sources. So we are expecting the solutions to be longer. Okay, let's proceed. The subject matter for this morning will be alternating current circuit. This is now lesson number 29. And lesson number 29 is example problem of Nodal's theorem. We are given three voltage sources and we are looking for the current delivered to the load, isobel. Okay, let's try to discuss the figure. We are given three voltage sources and they are connected in parallel, so this should be A1, A2, A3, internal impedance number 1, number 2, number 3, and across this node here. This is a node. Okay, we connected the load. Okay, and the problem is asking what will be the current delivered to the load, okay, with the given specifications. These are the specifications. A1 is 550 angle 0, A2 is 540 angle 0, A3 is 530 angle 0 degree. Internal impedance number 1 is this one here. We got the rectangular, this is the polar. Internal impedance number 2, this is the rectangular, this is the polar. Internal impedance number 3, this is the rectangular equivalent and this will be the polar. And the load is 100 ohms, angle 60 degrees. So with these specifications, okay, what will be isobel equal to? Oh, this is a complicated problem. If we haven't, derived the formula on how to compute for the voltage across this, okay, it's a complicated solution. So it's either we are using the so-called superposition theorem or the Nodal's theorem. But under the Nodal's theorem, okay, it is much more simpler because we are now given the equation for the computation of the voltage across this. Okay, and if we try to divide B sub L, the nodal voltage, by the load C sub L, we can compute for the current. Okay, so it's just a matter of computing the values of all these parameters over here. That is E1 over C1, E2 over C2, E3 over C3, plus the summation vectorial sum of 1 over C1, C2, C3, and C sub L. So it depends on how you bring out your solution. If you're not systematic enough, this should be a long solution, right? Because if you made one mistake on the sign, it's all wrong. Okay, let's proceed with the solution. For Nodal's theorem, if there are three voltage sources, the numerator should be 3. Okay. The last time around, we are missing A3 and C3. Okay. And 1 over C3, we are missing those ones. Because we are only given 2 voltage sources. But for this morning, we are given 3 voltage sources. So the numerator should have an additional thing A3 over C3. And the bottom portion should be 1 over C3. This is similar to the last lesson, except that the voltage sources from the past lesson is only 2 voltage sources. We are missing this one here, and this C3. But for this morning, we are given 3, so we added A3 over C3 and 1 over C3. Oh, it's easy. So if you know your equation, it's just a matter of computing this one. So, okay, at least you are good with using your calculator. And the main problem here is the conversion from polar to rectangular. Okay, just be accurate, because if you are not accurate, you make one mistake sign, it's all wrong. Okay, so the solution of this, it will be, we compute this one individually. Okay, we don't go per substituting values, then try to simplify. Okay, you'll go crazy. So what we will do, we'll take A1 over C1. We will take the evaluation of the numerator separately. So A1 over C1, 550 angle 0, 0.522, 73.3. We are now given the polar of E1. We are now given the polar of C1. The polar equivalent is this. Okay. So if you are on the board exams, if you are given a rectangular, convert it immediately to polar, because there are some operations which require the value to be in polar form. Since we are dividing, okay, the simplest solution is should be a polar over a polar, right? So after the computation, it is this. We are now given the rectangular. We divide this one, it 1053. Okay, converting this, take cosine multiplied by this, that will be the real part. Take the sine multiplied by 1053, that will be the imaginary part. As simple as that one. But be accurate, okay, and write legibly, so the examiner could read your solution. 8 over C2, this should be 540 angle 0 over 0.180 to 56.3. We are given the polar of C2. Right? So polar over polar. Okay? 2996, negative 56.3. 0 minus this, it goes up. It should be negative. Take the cosine multiplied by this, that will be the real part. Take the sine multiplied by this, that will be the imaginary part. The sign should be negative, this is negative. E3 over C3. E3 is 530 angle 0. The value of C3 in terms of polar is 0.2163, angle 56.3. 530 over 0.2163, that will be 2450. We raise this up, this should be negative 56.3 degrees. Converting to rectangular, take the cosine multiplied by this will be the real part. Okay? Because later on, we will be adding this one. That's why after the division, I converted it immediately ASAP to rectangular. Okay? Take the sine of this, multiplied by 2450, it will be 2038. But it must be negative. Okay, let's go with the bottom portion. 1 over C1. 1 over C1, we are given C1 in terms of polar, right? 1 over this, 1.9157. This goes up, negative 73.3, converting to rectangular, 0.55 minus J, 1.8349, rectangular. Why I changed to rectangular? Later on, upon reaching the denominator, we will again take the sum. So it's a must that we should convert all the things under the denominator in rectangular form. Okay, 1 over C2. 1 over 0.1802. Okay, this goes up. 5.55 negative angle negative 56.3. Take cosine multiplied by this should be the real part. Take the sine multiplied by the magnitude, this should be the imaginary part. So this is the rectangular equivalent of 1 over C2. 1 over C3. Okay, so there's nothing hard about it. It's just that be patient in the computation of the rectangular to polar and vice versa. Okay, 1 over C3, 1 over C3 is 0.2163, angle 56.3. 1 over 0.2163, 4.623. This goes up, negative 56.3. Take cosine times this. This is the real part, 2.565. Right? Take the sine of 56.3 negative. Okay? Multiplied by 4.623, the magnitude is 3.846. The sign should be negative. Okay? So we are given again the rectangular equivalent of C3. I am preparing for the vectorial sum on the denominator. That's why I converted all the magnitude to rectangular. 1 over CL, we are on this. 1 over 100 angle 60. 1 over 100 is 0.01. We raise this up. This will be negative 60. Take cosine times 0.001. It will be 0.005. Take the sine. Okay, it's actually 0.866 times 0.01. So this is negative j. It should be negative because the angle is negative. Negative 0.00866. Okay, rectangular. Okay. Let's try to take the summation of the numerator. E1 over C1, E2 over C2 plus E3 over C3. I didn't place it here anymore. So what I did is that where's E1 over C1? I take the sum of this, 302, okay, 1662 plus 2450, no, 1359. The sum is actually 3324.98. That's the real part. And for the imaginary part, this is negative, negative, is negative. So just take the sum of 1009, 2493, and 2038. That will be 5540.83. Converting this to polar, because later on we will divide, right? I was anticipating that we will divide after the simplification. Okay. This should be 6461, angle negative 59 degrees. 5540 is greater than 3324. If we take the ratio, it's more than 1. So our angle here is greater than 45 degrees, but it should be negative. Our angle is negative 59 degrees. The magnitude now will be take cosine, divide that to 3324. What comes out is 6461. We can check it. You display 59, okay, take the cosine. We take the reciprocal of that times the real part, 3324.98. Okay, it's 6451, 61. Okay, then we take the summation of the denominator. 1 over C1, 1 over C2, 1 over C3 plus 1 over CL. I didn't place it here anymore. I just placed the summation. So what I did, it's just easy. Where's 1 over C1? You take 0.55, you add that to 3.079, you add that to 2.565, you add that to 0.005, the real part will be 6.199. Okay, and for the imaginary part, let us see, this negative, this is negative, negative, and it's negative. See, there's no problem. The overall sign of the imaginary part will be minus. So we will take 1.8349, we will take 4.616, we will take 3.846, then we will add 0.00866. The magnitude will be 10 point something. Okay, nobody contradicts. They are all negative, so the overall sign is negative. So 10 divided by 6.199, it's greater than 45 degrees, right? What comes out is negative 59 degrees. Okay? And if you try to take the cosine of this, we divide that to 6.199, it should be 12.0263. Okay? 59 degrees cosine. We divide that to the value 6.199 to get the magnitude. 1 over x times 6.199. 12.0263. Okay, so this is 12.0263. You can either use the cosine value, the sine value, or use the Pythagoras principle. Okay? So we now know the summation of the denominator, we now know the summation of the numerator. They are both in polar now, so B sub L now, we go back to this. Okay? It should be the ratio, the polar of the numerator, 6461 angle negative 59 degrees. And the summation of the total denominator is 12.0263 angle negative 59 degrees. Okay? 6461 divided by this is 537.3. Okay? Minus 59. We bring this up, plus 59. The angle will be 0. The angle of B sub L will be 0 degree volt. Okay? Why? These are all in 0, right? They are reference vector. So I sub L now, we have computed the value of B sub L already. My ink is gone. We divide B sub L by C sub L. So the last part of the solution will be 537.3 angle 0 degree, and the value of C sub L is 100 ohms angle 60 degrees. 100 angle 60 degrees. And the magnitude of the current drawn by I sub L will be 5.373 angle negative 60 degrees. We raise this up, amperes. So how do we know if this answer is correct? Okay, like what I did, guys, I got the superposition theorem solution on my notes. Okay, so what I did, by using the superposition theorem, okay, I shorted these two. I computed by the current drawn by this without the two voltage sources. Okay, the first current is this value here, 0.876 negative 74.33 degrees. Then again, I shorted number 1 and number 3. So I computed for the current due to E2. What comes out is 2.4914 negative 57.34 degrees. Then I shorted voltage sources number 1, number 2. I consider E3. The current consumed by this due to E3 is 2.0375 negative 57.3 degrees. And if we try to take the summation of this, okay, summation. So there should be a real part, imaginary part, real part, imaginary part, real part, imaginary part. I have it in my notes, I just didn't place it here. If we take the summation, okay, the magnitude is 5.373 degrees, okay, negative 60 degrees, amperes. So by using the superposition theorem, okay, the current is the same, 5.373, the angle is negative 60 degrees, 5.373, the angle is negative 60 degree amperes. But the superposition theorem is longer because we consider two voltage sources. You simplify the circuit, compute for the current due to source number 1. That's a long process. And consider again E2, okay, try to compute for the current due to E2, that's again a long process. Okay, it's in my notes. Then compute E3, compute again the current due to E3, okay. Actually, what comes out are these. Okay, then try to take the summation. Of course, you convert this to rectangular, rectangular, rectangular. Then take all the real parts, take all the imaginary parts, then try to change it to polar form. The magnitude is 5.373 angle negative 60 degree amperes. Okay, that's it, guys. That's an example problem of a Nodal's theorem involving three voltage sources supplying a load to a common load C sub L. So for those of you who are taking up electrical engineering, okay, this is for you guys. If you want to subscribe to my channel is at youtube.com/@ProfDavidJ. If you want to share it, please click share. Okay, the next time around, we will be having a new topic. I think, I will just tell you the next time around. It's another topic, it's not Nodals anymore. So we are now through with Nodals. Okay, good morning from Los Angeles. This is Professor David J.